All right, so today's lesson is on polar graphs. The rectangular coordinate system, up until now, we have been using and graphing in rectangular. That means we have the x and we have the y, and to get to an ordered pair, you use x and then y. How far you went left or right, and then how far you went up and down. These are called rectangular coordinates and are of the form x, y, and pretty much everything you've done up until now has been in the rectangular coordinate system. Now we're going to change that. We're going to talk about the polar coordinate system. Sometimes it is simpler to use the polar coordinate system. The foundation of the polar coordinate system is a horizontal ray. Here is our horizontal ray. This is called the polar axis. Notice it's very similar to the x-axis, the positive side. That extends to the right. The end point of the ray is called the pole. That's very much like the origin. And points are of the form r comma theta. Instead of an x and a y, we have an r and we have a theta. In the polar coordinate system, here is the polar axis, here's the pole, and then here is our r. This is the distance that we go out at a given theta. Again, the point is r theta. More on the points later. We're not going to focus too much on those now. So there's a relationship between the polar and the rectangular systems. They are similar, they go together. Notice for rectangular we have the x and then we have the y, and it makes a nice pretty right triangle here. And then we have our hypotenuse, or our r, our radius from the polar system. There is a relationship here between them. If you're taking a look at it and we're talking about the x and we want a relationship for the x, we can see, okay, well, if I've got theta and I want to know about x, well, this is a right triangle. And I could maybe use some of my trig functions like we discussed yesterday in our trig review there. So if I wanted to use the y, I'd have the opposite and the hypotenuse. So the y might be sine there. So I know that sine of theta would equal y divided by r. So if you wanted to get y by itself, we just multiply by r. So y equals r times sine of theta. Not so important for today, but in the future. If we want to talk about x, well, x is the adjacent side. So I have the adjacent side and the hypotenuse. So I'm going to be talking about cosine. So cosine of theta would equal my adjacent divided by hypotenuse, which is x divided by r. And again, if I want to get x by itself, I would multiply by r to get it off the bottom. So I have x equals r cosine of theta. Again, two formulas that are important for the relationship between rectangular and polar coordinates. Not really going to use them today. We'll be using them later on in this unit. In the same way, again, we've still got that right triangle here. Still got that right triangle. I see that I have x squared plus y squared equals, oh, you guessed it, the Pythagorean theorem. X squared plus y squared equals r squared. Straight up Pythagorean theorem. There's nothing new about it except for we changed the letters that we're using. That's all. Tangent is very similar in that you have theta and you have the opposite and the adjacent. And hey, look, it's y over x, which is exactly what we talked about yesterday in our trig review notes. That relationship is always there. That's why we talk about it. So again, these four formulas are very important. Excuse me. They're very important for later in this unit, but not so important for the section we're talking about now. Just to give you an idea of the polar coordinate system and where it comes from and what we're talking about. So general equations for circles in polar form. This is a very kind of a lot going on the screen, so don't be too overwhelmed here. So circles are very easy in polar, and they're of the form r equals a sine, or r equals negative a sine, or r equals a cosine, or r equals negative a sine cosine. Either way, it's much easier than in standard form in rectangular coordinates. Notice the a value is always the diameter. The a value is the diameter. Sine circles will always be along the y-axis because sine is the y-coordinate, so it's always along the y-axis there. And any of them that have a cosine in them will always be along the x-axis because cosine is the x when we're talking about our unit circle there. So let's try one here. So it says identify the center and graph r equals 6 sine of theta. r equals 6 sine of theta. So it's important to start out and identify along which axis are we going to be at here. So it's sine and it's positive. So I know it's a little hard to look at, and this is really overwhelming for a lot of people. But just remember that embedded inside of the polar coordinates is the normal rectangular system. Our XY coordinate plane is still in there. And you'll see right there in the center, I didn't do a great job drawing this here, you'll see in the center, that is our pole, also known as the origin in rectangular. So, I'm going to erase this here, it's just bothering me, I did a really bad job drawing that. Alright, so there, I don't think I did any better that time, that's okay. Alright, so it is a positive sign. So for positive sign, that means I'm going to start at the pole and put a dot. And because the diameter is 6, I'm going to count up 1, 2, 3, 4, 5, 6 and put a dot. And then I'm going to try my very best to make a circle. And I know it is very hard to draw a circle on these kinds of graphs. Just try your best here. There is my circle. An important part that I need to write down is the center. And when I write down the center, I can either count it out or I can use my formula. My formula said for sine, it's 0, a divided by 2. Well, that means I have 0, 6 divided by 2 is 3. But sure enough, if I look, 0, 3, that's 0. I didn't go side to side. Then I went up 1, 2, 3. There's my center. Sure enough, that is my center. So you can either use the formula or you can count it out yourself. Totally up to you. For example number 2, we have r equals -4 sine of theta. So very similar to the last example with two main differences. This time we have a 4 instead of a 6, and it's negative. That negative is important. Again, we have our embedded xy axis. Again, I'm doing a bad job drawing it. Sorry about that. The main difference here is because sine is negative. Well, sine means we're on the y-axis. And because sine is negative, instead of going up, we're going to go down. And we're going to count. We're going to put our dot on the pole, and then we count down 1, 2, 3, 4, put a dot, and there again is my circle. And try your best to actually go through the points, unlike I did, and again to get that circle there. Always make sure you write down the center, and we can use the formula that we used before, no big deal, which was 0, a divided by 2, so -4 divided by 2 is -2. And again, if you notice, 0, -1, 2, there is the center of my circle. I didn't do a great job drawing it, but you get the idea. So sine means you're using or along the y-axis. If it's positive sign, you go up. If it's negative sign, you go down. Just like positive y is up and negative y is down. Example number 3. This time, we're talking about cosine. And cosine has to do with the x-axis. So that means cosine is going to be along the x-axis. And because cosine is positive, that means we're on the positive side of the x-axis. Again, we can go ahead and put a point on the pole there. And then we have a 7. So we're going to have a diameter of 7. So we're going to count out 1, 2, 3, 4, 5, 6, 7. Got a dot. Again, we went right because it is a positive cosine. That's positive x direction. So there I can try my very best to draw a circle. The center this time, if you look at it, I went to the right and then didn't go up and down. So my center, sorry about that, I'm having trouble writing the word center. My center is going to be 7 divided by 2, 0, which we can see we're over here at 1, 2, 3, 3.5, or 7 over 2, 0. That is in fact the point of my center. So don't overthink the polar grid too much. I know it looks a little scary, but that 7 over 2, 0 is just the same as it would be in rectangular. If the polar coordinates weren't there, it would still be the same location. For example number 4, this time we have a negative cosine. Alright, so when we had a negative sign, we went down because sine was in the y direction. So having a negative cosine, instead of going in the positive x direction, we're going to go in the negative x direction. So we put a dot on the pole, right there in the center, that origin. And then we count to the left. 1, 2, 3, 4, 5. Got a dot. And do my best to draw a circle. The center again is going to be right between there, but I went to the left. So for my center, I'm going to have -5 divided by 2, 0, which I can see. -1, 2, 2.50. There it is. There's my negative 5/2 or negative 2.50. That is in fact my center. So use the formula if you want, or you can just count it out. Very similar to how we did conics, you can just count it out, it's no big deal. As you can tell, circles in polar are way easier. The formula is much simpler, takes way less effort. Only thing you got to write down is the center there. All right, so next up we have cardioids. Next up we have cardioids. And the key word in cardioid is in cardio. Cardio relates to things that get your heart rate moving. And cardioids, so people say they look like hearts. They look like hearts with kind of a rounded end to them, and that I agree with. But personally, it looks a little more like a butt to me. Whenever I draw a cardioid, it kind of looks like a butt. Remember, don't make it pointy at the end. It does have a nice round part to it. Does always have a nice round point, and it always touches the pole there. It's always going to touch the pole. So here, there's very similar to the circle formula, because the circle formula is r equals plus or minus a sine theta, or r equals plus or minus a cosine theta. But this time it's a plus or minus a sine of theta, or a plus or minus a cosine theta. Notice the length of the cardioid is the absolute value of 2a, so it's always the positive version. Always the positive version. And for sine, it's always going to be along the y-axis, and for cosine, it's always going to be along the x-axis, just like with circles. And just like with circles, that's the difference between the plus and the minus. If it is a positive sign, that means we go up, because sine is y, and positive y is in the up direction. If it is a negative sign, that means we're going to go down, because y is negative in the down direction. If it is cosine, that's our x. So if it is positive, we go to the right because that is the positive x motion, or if it is negative, we go to the left because that is negative x motion. Again, it always touches the pole, and try not to make it pointy at the bottom. So for number 5, we have r equals 6 plus 6. All right, so here we are on example number 5. Example number 5 is a cardioid. And when you see that, we have 6 plus 6 cosine theta. We know it's a cardioid because the 6's are both the same. It would be a circle if we only saw 6 cosine of theta, but here we have 6 plus 6 cosine theta, so we know we have a cardioid. And when that happens, we're going to talk about our length. So length equals the absolute value of 2 times a. Notice our a value is 6, so we have the absolute value of 12 because 2 times 6 is 12. And the absolute value of 12, of course, is 12. So we know we're going to touch the pole. So I go ahead and I put a dot on the pole, and then I count out 1, 2, 3, 4, 5, 6, 7, 8. Okay, wait a minute. I have to go 12 in the positive x direction, and I know I'm going in the positive x direction because I have a cosine, which tells me x, and I have a plus sign, which tells me in the positive x direction. However, I only have 8 units, so I can't count 12. So what that means is I need to scale my graph and give me some indication that 1 unit in this case will let it equal 2. And you can show it by counting by 2's on your graph if you like. Give me some indication. But we still have to go to 12. We just don't have 12 boxes, so we're going to scale our graph. So always look out for that. A lot of times with polar, you have to rescale the graph, and people get confused about that. So make sure you're very clear about what units you're counting to. So we count out to 12 on the positive x-axis. Again, we know it's x because of cosine, positive because of the plus sign, so we go to the right. Then we're going to talk about the width of my cardioid. And the width of the cardioid is always the a value. Here that is 6, so I'm going to count up 6, keeping in mind I'm counting by 2's here. So 2, 4, 6, got a dot. Then I go down 2, 4, 6, got a dot. And there are the 4 main points of my cardioid. So I'm going to do my very best here. Do my very best to draw a curved, not pointy cardioid. A curved, not pointy cardioid. They are difficult to draw. I do understand. Take a minute, try your best. Notice I went through. It has the right width on each side. It's curved, and it's not pointy at the end. It is not pointy at the end. Example number 5 is similar to example number 6. Main difference here is that we have a negative instead of a positive. So instead of going in the positive x direction, we're going to go in the negative x direction. I know it's the x direction because of the cosine, and I know it's negative because of that negative sign. We can go ahead and talk about length again. And for the length, it's the absolute value of 2 times A. And in this case, A is 5. So 2 times 5 is 10. And what's the absolute value of 10? Sure enough, it is 10. Very good. Similar to the last problem, I don't have 10 units. If I count them all out, I only have 8. So I have to rescale my graph. So to do that, again, I've got 2, 4, 6, 8, 10. Notice it's not negative. Notice it's not negative. The circles, that whole circle is 2, that whole circle is 4, that whole circle is 6. You're not actually making negative numbers. That's a main difference with rectangular and polar. More on that in a little while. So I'm going to put a dot at the pole and then count in the negative x direction because of the negative sign. 2, 4, 6, 8, 10, got a dot. And now I need to discuss the width. The width is 5, so I'm going to count up 5 and down 5. Again, I have scaled my graph, so each one is actually not 5, but 2.5. So I'm going to go up 2, 4, 5, got a dot, down 2, 4, 5, got a dot. So I can do my very best to make my nice curved graph there. It's not pointy, it's not pointy. Again, supposed to look like a heart, it really looks more like a butt if you ask me, but you know, that's fine. Example number 7, this time we have sine. So when we talk about the length, always do it first there. We have 2 times 8, which gives me 16, and the absolute value of 16 is 16. I already know I don't have 16 squares. No matter which direction I'm counting, I don't have 16 squares. So I'm going to go ahead and I'm going to scale my graph again, keeping in mind it is sine this time, so I'm going in the y direction, and I know I'm going up because it has a plus sign. So I'm going to go 2, 4, 6, 8, 10, 12, 14 there, 16 up there, good enough. Got a dot on the pole. And of course I need to talk about how wide the graph is going to be. So that 8 is my width. So this time I'm going to side 8, but I've been scaled by 2. So 2, 4, 6, 8. 2, 4, 6, 8. Those are my 4 points. And then I can just do my very best to draw. Well, this one isn't terribly good. It's kind of asymmetrical, but you get the idea. And if you need to turn your paper so it makes it easier to draw, please feel free to do so. Remember, the A value is always the width. The A value is always the width. If you want to pause the video and see if you can try example number 8 on your own, I encourage you to do so now. Alright, so assuming you tried it out, we'll go ahead and go through it here. So we have the length is the absolute value of 2a, so that's 2 times 4, which is 8. Absolute value of 8 is 8. This time, I don't have to scale my graph because I do have 8 units. I know I'm going along the y-axis because it's sine, and it's negative, so I'm going down. So I put a dot on the pole, and then I count 1, 2, 3, 4, 5, 6, 7, 8, got a dot. And then I need to worry about the width. The width in this case is 4. So I count out 1, 2, 3, 4. Notice I'm not scaled, so I'm counting the full 4. 1, 2, 3, 4. There I am. And again, try my very best to make it not pointed. If it comes out a little pointy, that's fine. It just happens from time to time. So far we have circles and we have cardioids. Next up is the fun one. Next up here, we have a limacon, and the limacon should actually have a little caveat under the C there. I forget exactly what it's called, but it's called a limacon. A limacon. Not a limacon or a limacon, a limacon. It is a limacon. Limacons are kind of like cardioids. They are very similar in their formula, except that A and B are different numbers. A and B are different numbers. So for a cardioid, to find the length, we did the absolute value of 2 times A because the A values were the same. But to find the length for a limacon, we take the absolute value of A and add it to the absolute value of B. We just take the total part. Now there are actually 2 types of limacons. We have what's called a loop, which has a general form of having a loop inwards into the shape. Or we have a bump out, and a bump out kind of pushes out, and it kind of has a little dimple, and it pushes away from the pole. it pushes away from the pole. So bump outs do not touch the pole. That's important to point out there. Bump outs do not touch the pole. And the way we tell the difference between a bump out and a loop is based on which one's bigger. So it has a bump out if it has a bump out. Let's see. So it has a loop if A is little. If A is less than B, then it has a loop. If A is less than B, then it has a loop. It has a bump out if A is bigger than B. It has a bump out if A is bigger than B. And the length of the loop and the length of the bump out are basically the bigger one minus the smaller one, the bigger one minus the smaller one, whichever one that may be. So it has a loop when A is little. It has a loop when A is little, when A is less than B. Again, if it has sine, it'll be on the y-axis. If it has cosine, it'll be along the x-axis. Let's try the fun ones here. Identify the length and if it is a loop or a bump out, and its length. Then graph r equals 4 plus 6 cosine theta. So first things first, I know that it's a limacon because I have two different numbers. If I had a 4 and a 4 or a 6 and a 6, then it would be a cardioid and we wouldn't have to worry about whether it had a loop or a bump out. But I know that it's a limacon because I have two different numbers here. And I can go ahead and talk about the length of the limacon as a whole. It's just going to be 4 plus 6, and 4 plus 6 gives me a length of 10. Then I need to determine if it's going to be a loop or it's going to be a bump out. So going back here, it has a loop if A is less than B. So A is the first one, B is the second one. So is A less than B? Yes, it is. So it's going to have a loop. It's going to have a loop. And if you want the length of that loop, all right, so according to our formula, the length of the loop here is B minus A, the big one minus the little one there. So I'm going to have B minus A, so 6 minus 4, which gives me 2. I'm now ready to draw my limacon. So I can come over here. Oh no, it's got a length of 10. I don't have 10, so I'm going to have to scale it. So I can come in and say, all right, 2, 4, 6, 8, 10, whatever, doesn't matter. Now I went ahead and labeled along the y-axis. I did that this time to get it out of the way because I'm going to be along the x-axis. So I'm along the x-axis because it has a cosine, and I know I'm going in the positive x direction because it has a plus sign. So I'm going to count out 2, 4, 6, 8, 10, got a dot. The loop has a length of 2, and to do that, you go from the pole and count in 1, 2, or in this case, just 1 unit, because 1 unit is 2. So I counted in 2. Towards the length, the same direction towards the length. All right, still got to worry about my width here, and my width is always that A value, so it's going to be 4. So from the pole, up 2, 4, got a dot. Down 2, 4, got a dot. And this is the tricky one where people get a little bit confused on how to draw it. So be very careful here. I start at the bottom, go up to the width, go down, and there's my loop. My loop goes towards the same direction that I drew the length. Sometimes it touches the pole, sometimes it doesn't. We're not really going to worry too much about that. What I am worried about is that you have the width correct, that you have the length of the loop correct, and the length of the limacon itself there. All right, I know these are tricky. We're going to try another one. All right, number 10. Number 10 here. Again, we have different numbers. That's how we know it's going to be a limacon. And for the length of the whole thing, regardless of a loop or a bump out, it's going to be 2 plus 3, which gives me 5. So the length of the whole thing is... All right, so here we are, example number 10. Again, we know we have a limacon because we have different numbers. The A is little, which means we're going to have a loop. Before we get to that, we can talk about the length of the entire limacon, which is going to be 2 plus 3, which gives us that 5. We know we have a loop, again, because the A value is smaller than the B value. So we have a loop, and we are going to have 3 minus 2, which gives us a length of 1. It's cosine, so we're going in the x direction, and we have a negative sign, which means we're going in the negative x direction. We start at the pole and we count out 1, 2, 3, 4, 5. There's the length of my limacon, And for the loop, again, we start from the pole. We count 1 towards that length, towards where I already counted. There's my 1. Then we got to talk about the width. Remember, the A value is always the width. So 2 is my width. So from the pole, we count out 1, 2, and then down 1, 2. Do your very best. Again, I know it is difficult. Make your loop of the correct length-ish. And again, try not to make it pointy, but if you do a little bit, that's okay. Example number 11. Again, A is little. We have an A and a B value because they're different. That's what tells me it's a limacon. So the length is going to be 1 plus 2, which gives me that 3. I know it's a loop because the A value is smaller than the B value. So I know it's a loop, and it's going to have a length of 1 again. This time I have sign, so I'm going along the y-axis, and it's a positive sign, so I'm going in the positive y direction. So from the pole I count up 1, 2, 3, and I have a dot. And the loop, again, towards that length, I'm going to have my loop length of 1. The width of this one is also 1, so 1 to the left and 1 to the right. And then I just do my very best to draw my limacon. I know they're a little funny and they don't have to be super perfect, but main information is the length and that it's a loop and that the length of the loop. Also look out for your width there. Number 12, it's very similar except this time we have sign and it's negative. Again, A is still little. If we want to talk about the length of the entire thing, it's 3 plus 4, that gives me 7. I know I have a loop because the 3 is little, and 4 minus 3 gives me a loop length of 1. I'm going in the y direction, and then the negative y direction because it's negative sign, so I'm going down. So from the pole I count 1, 2, 3, 4, 5, 6, 7, got a dot. Then my loop is 1 towards that, and I have a width of 3. So from the pole I count 1, 2, 3, and then 1, 2, 3. Try your very best to make it curved and to hit all of your points. If you want to turn your paper, that is okay. I know that they are difficult to draw. It kind of takes just some practice, but you'll get it. All right, number 13 is a little bit different. Number 13 is a little bit different. You'll notice this time it's still a limacon because we have a 5 and a 4, so it's not a cardioid, but the A is bigger this time. And when the A is bigger, it is not a loop. When the A is bigger, it is not a loop. Remember, you've got your formulas over here if you ever forget, right? When A is little, you have a loop. When A is big, you have a bump out. All right, so coming on back to number 13 here. Again, we find our length in the exact same way. It's going to be 5 plus 4 gives us 9. Then we know we have a bump out, again, because the A value is big. If the A value is big, you've got to have a bump out. So for the length of the bump out, I'm going to say 5 minus 4 gives me 1. It's always the bigger one minus the smaller one, whatever that means. Cosine tells me I'm along the x-axis. Negative tells me I'm in the negative x direction. So for the length, I've got to count out 9. But I only have 8 units. So again, I'm going to scale my information. And I might do it off to the side over here this time just so you can see that this is 2, 4, 6, 8, 10. Again, they go all the way around the circle to keep you from having to kind of write in the way and maybe you get confused by your numbers or whatever it is. You can write me a note off to the side. Just let me know that you've scaled your graph. So in the negative x direction, I'm going to count out 2, 4, 6, 8. Oh, there's 9. Now, it's a bump out, and this is different than a loop. It doesn't go towards the length. It goes the opposite direction. So I'm going to count out 1, and it's kind of going to look like a half here, because remember we scaled it, so half of that circle would give me the 1 instead of the 1/2 there. All right, so again we have the loop, or not the loop, excuse me, the width. So I count out 2, 4, 5, got a dot. Count down 2, 4, 5, got a dot. This one does not have a loop. Does not have a loop. Instead, it kind of looks like it's pushed out a little bit. It still vaguely has kind of a heart shape. Sometimes they call it a dimple, where it just pushes in right there. Sometimes they call it a dimple there. And you can see that it just pushes in. So it's different than a loop because a loop comes towards the length and a bump out bumps it out. It bumps it the opposite direction. It's kind of why they call it a bump out. So for number 14, last one. Again, we know we have a Lima sign because our leading coefficients are different. Remember, if you don't see a number, you assume it's a 1. So the total length is going to be 3 plus 1 to give me 4. I know it's a bump out because A is big, so I've got a bump out. And for the length of my bump out, it's 3 minus 1, which will give me 2. Sine means I'm along the y-axis. It's a positive sign, which means I'm in the positive y direction. So I start from the pole, and I count 1, 2, 3, 4, and have a dot. Remember, my bump out goes the opposite direction, so I don't count out 1. I count out 2 in the opposite direction. Then my width is going to be 3, so 1, 2, 3 to the left, 1, 2, 3 to the right. And again, it kind of just looks, it almost looks like a circle or a cardioid that's just been kind of like pushed out, where they take what usually comes in and they just push it out, and it makes a little dimple there. So look out, I know they're a little hard to draw, but do your very best, and good luck with our day 1 polar graphs. Oh, that's it? All right, so if you have any questions, just rewind, hit me up on Remind, let me know. All right, good night.